Hello, everyone. Well, I don't know how familiar you are with AI, especially the students. When I was a student, there was a breakthrough in AI every 5 years or so. When I started to do research, there was a breakthrough in AI every year. And now it seems that there's a breakthrough in AI every month. But the thing is, how well are we measuring these breakthroughs in AI? Because probably you see that on the news, the things that are possible today with AI. And when I was aware that there was a project trying to create, or actually creating, a platform for AI evaluation and AI experimentation, I think this is a long-awaited thing in AI. And today we have the pleasure of having not only one person talking about the project Malmo, but we have the brain and the spirit of the project. And I think that the details of the project are going to be explained much better from her than from me, but I've been playing with the platform, so I can tell there are many great things about this platform and many possibilities, but I think it is much better that Katja Hofmann from Microsoft Research, she can just explain to us what this platform is about. Okay, thank you, Katja.
Thank you, Jose, for the kind introduction, and thank you all for coming. It's a great pleasure to be here and tell you about Project Malmo and what it means for AI experimentation. During my talk, please feel free to ask questions at any point in time. So we'll start with the quest for artificial intelligence. This quest really started in the 50s with the great pioneer of computing and artificial intelligence, Alan Turing, that I'm sure you're very familiar with. So in the 1950s, Alan Turing started to really think through what could be done in the future with those computing devices that people were just starting to develop. And he was the first to really formulate this question and these ideas around whether it's possible to develop machines that are intelligent, whether we can develop machines that think. And since then, there has been a huge amount of research and development towards developing machines that in some way have human abilities, so that somehow are like us, that show intelligence, that show thinking like humans. But if we look at what humans can do, there's this huge range of human abilities. There's not a single thing where we can say, oh, if we only build a machine that can see, then we actually have a machine that has the same abilities as a human. Instead, humans can learn, they think, they can compute, understand, read, they learn to play the piano or make plans and recognize emotions. So there's this huge breadth of abilities that we have as human beings. And over the past decades, people have invested a lot of work. There's been amazing research and engineering efforts into replicating some of those human abilities and create machines that have those abilities. So if we look at what machine abilities we have today, people have developed machines that can see. When I show a machine a picture like this, maybe the machine wouldn't recognize that this is an image of some of the people in my team, but we have face recognition software that can very easily detect that there are faces in this image and where they are located. And already we have this technology in every single mobile phone, every single camera to help us take that best snapshot. We have now machines that can speak. For example, a Skype translator is a plugin into Skype that can listen to natural human language in real time and translate that to another language. So for example, you speak English, it's translated on the fly into Arabic. So you can already have machines that can listen and that translate and speak natural human language, enabling people to communicate across language barriers. So individually, each of those abilities, each of those machines that have been developed to replicate human abilities is an amazing feat of engineering and research. However, when we talk about intelligence, we're not just measuring the ability of a human to speak, for example, or just the ability to see. Instead, when we talk about intelligence, we are really talking about some agent's ability to achieve a wide range of goals in a wide range of environments. And when we talk about intelligence, what's really key is this generality, this ability to deal with anything that life throws in your way and to learn to achieve goals in whatever environment you encounter. Now, if we take that as the goal of understanding intelligence, or maybe even building machines that exhibit intelligence, then we can ask ourselves, in those decades of research and making progress towards machines that see and speak, have we actually made progress towards developing something that is intelligence? Have we made progress towards artificial general intelligence, as you will? And the answer is, well, maybe. It's not even clear whether we would be able to measure whether we are making progress in this direction. And this question of how to measure whether we are making progress, whether we are actually developing machines that are becoming more and more intelligent, is where Minecraft and the Malmo platform that our team has developed can really help answer some of those key questions. When we think about what enables progress in any research area, in any scientific area, then experimentation is key. Experimentation allows us to make rapid progress because experimentation creates the tools that allows us to measure whether we are making progress. It allows us to quickly prototype our ideas and compare them to other ideas. They allow us to test hypotheses. And the faster we can experiment, the faster we can make progress in any scientific area. So this is why when we talk about progress in AI, it's really key that we are able to measure whether we are making progress, and it's key that we can measure and experiment as quickly as possible. This is the need that Minecraft can address. How many people here in the room have played Minecraft before? Can I see a show of hands? Almost everyone, fantastic. Okay, so you definitely know what I'm talking about. So for the 3 or 4 people who aren't familiar with Minecraft yet, Minecraft is an open-ended, so-called sandbox game where, do you have any questions? Where there is no single given goal. Instead, people go into this world, they explore, they create crazy structures, they can socialize and play with others. And in this way, because it's so open-ended, the game provides an infinite variety of possible goals that we can expose our AI agents to. The worlds are procedurally generated. They're 3D worlds that agents experience from a first-person perspective. So it's very much like the real world in that respect. The world has physics. It's simpler physics, of course, than in the real world, but they are coherent, and this allows an agent interacting with this world to learn about the principles of the world and to generalize to new situations where knowledge about those physics or common sense knowledge might be applicable. So based on this platform and based on seeing that it provides this platform for a wide range of tasks and experimental settings, what me and my team were trying to look at is whether we can make it very, very easy for experimenters to connect their agents into the game and run experiments as quickly as possible and as flexibly as possible. Kind of as background, in the past, people have thought very much about what kinds of characteristics they would require for a generic experimentation platform for artificial general intelligence. And most recent work by Laird and Gray 3 in 2010 and Adams and colleagues in 2012 came to the conclusion that these are the key characteristics that such an environment would need to provide. So they were asking for a complex environment with diverse structure and diverse interaction. So this can be seen that in Minecraft we can use the full complexity, rich structure, and interactions that are provided by the Minecraft game. And they were asking for an open and dynamic environment to ensure that an agent in this environment cannot just memorize everything that might be happening and then memorize the optimal responses to that. Similarly, in Minecraft, we have open-ended worlds that are procedurally generated, so you can always create something that the agent hasn't seen before. It's important that there are task-relevant regularities, and these regularities really allow an agent to learn how to generalize to new tasks or new goals within the same environment. So this is very much related to the common sense knowledge that I mentioned. And again, here, this is similar to the real world in the sense that there you can create tasks that have a certain hierarchy. In order to build a structure, you need to know how to walk, how to take blocks, how to place blocks. So there's a lot of this reuse and ability to develop common sense knowledge. It's important that other agents impact performance, and this is provided by this ability to have several agents in the same Minecraft world. Those agents can collaborate or fight each other, so there's a wide range and richness in terms of the interactions between agents. There's a need to support complex, diverse, and novel tasks. Again, this is important because we don't want to develop agents that just memorize a single task. Instead, we want to develop agents that can acquire new knowledge and that solve problems in situations that they haven't encountered before. We require complex and limited interactions between agent, environment, and tasks. And again, the limitation here is important because we want there to be regularities. If anything could happen, there's nothing that the agent could learn. So it's really important that we have this relationship between something that is complex, but at the same time learnable. We want to be able to impose limited computational resources. And typically, this would be imposed in the sense of a natural limit on time. For example, if you require an agent to interact in real time, then there's a certain limitation on how much computation you can do for every possible step that you take. And finally, we would like to have environments where we can have long-term continual existence of agents. So this would be a scenario where agents interact with the Minecraft world over the course of days, weeks, or months, and we develop agents that can essentially do lifelong learning, that continue to improve their performance, continue to learn as they persist in this environment. Right. So based on those requirements, we built the Project Malmo platform. This platform is a platform for AI experimentation. It's built on top of Minecraft, and it's open source on GitHub. So we've made it open source in summer, and there are already thousands of people around the world actually using the platform, either just to learn about AI and, for example, reinforcement learning approaches, or to do their research on top of the platform. It's available on GitHub right here, so you can actually go there and try it out today. But what does the platform actually provide? There are a number of use cases and kind of design principles that I want to walk you through. And I'll give you two examples of how to create agents and how to create tasks in the Malmo platform. First of all, we wanted to make it as easy as possible to connect agents into the game. So we have created an intuitive yet powerful API that allows you to just focus on implementing an agent in the programming language of your choice. The barrier of entry to this is really low. You'll be able to see that it only takes a couple of lines of code to create a simple agent and have it interact with the Malmo environment. And the agent can be written in any of a wide variety of popular programming languages. So we support Java, .NET languages, C, C++, Python, Lua. And the platform is cross-platform, so it runs on Windows, Linux, and macOS. In addition to making it as easy as possible to create agents in the platform, we provide a set of tools for creating tasks. So what I really emphasized is that for enabling flexible experimentation, we need to be able to create new tasks very easily. And as soon as an agent completes the task, we need to be able to scale that up, make it more complex. And this creates this kind of gradient of complexity, taking current AI technology from the state of the art that we have today and building up tasks that are more and more complex and that allow us to push AI technology in the direction of more and more sophisticated, more and more flexible learning agents. Finally, the platform provides kind of a plug-and-play interface for building extensions of the platform. For example, different kinds of observation handlers, so different ways of providing what the agent experiences when they are in the Minecraft environment, can be simply, it's simpler to add new ones, and in this way extend the platform as desired and as required by the experimenter. On a high level, the platform consists of the following components. There's the Minecraft game itself, which consists of a client and a server process. This ensures that several agents or several players can connect to the same Minecraft world and interact with each other in this world. We use a so-called mod, which is kind of a plugin into the game that exposes the state of the Minecraft world to the Malmo API. And it exposes the following components. It exposes observations. Observations are the inputs to the agent. So that could be, for example, the pixels, just a screen that the agent can observe, or that could be some symbolic representations, such as the blocks that are located in the vicinity of the agent, or that could be natural language. We expose a chat observation handler, and it can also be a combination of all those. So when someone experiments with the platform, they can create agents that combine, for example, pixel images with natural language through chat, or with some kind of symbolic information about what's located in the environment of the agent. We also expose rewards. So rewards are usually designed by the person creating the experimentation task. And this can be used for example, developing reinforcement learning agents that learn from some kind of reward signal that they're trying to optimize. So for example, that could be as simple as giving a positive reward when the agent achieves a goal, or there could be some punishment for taking a longer route to the goal, things like that. Finally, the agent sends back commands to the environment. So this is how the agent takes actions in the environment through these so-called command handlers that allow the agent to send information back into the environment. And again, the command handlers, there's a variety of command handlers that can be extended and that can provide different levels of abstraction for the so-called action space of the agent. So for example, one action space could be discrete movement. So we could create an agent that has, at every point in time, 4 possible choices to take 1 step forward, 1 step backward, 1 step left, or 1 step to the right. Or we could create an agent that moves in continuous space with the so-called continuous action space, where they can move at a certain speed at any point in time into all possible directions, and where we expose this ability to look around the Minecraft world just like a human player would. So there's, again, a lot of choice in terms of what complexity the agent is exposed to. And this allows us to create tasks that exactly target the certain phenomenon or the particular kind of technique that we are looking to investigate in an experiment. So the observation, reward, and command handlers that I mentioned are exposed through an API to the user. And the user's code interacts only with this API in order to define the task that the agent needs to address and to develop the agent code to actually address the task. The Malmo platform comes with a set of example tasks and agents included. So that makes it easy to go in and try out what's already there, get a feeling for how to create an agent, how to make it interact with the environment, and then it's easy to build up on that towards more and more complex technologies. Okay. So let's look at 2 use cases. The first one is, how do we create a simple agent in this Minecraft environment? We are going to look at a kind of reinforcement learning formulation where the agent sends actions to the environment and it gets observations and rewards back. This is all the code that you need. Okay, I abbreviated it a little bit, but this is roughly what you need in order to create your first Malmo agent. The key bit here is to import Malmo agent. There's a typo there, I'm sorry. to import the API, the library that Project Malmo provides. We create an agent host, over here, that kind of manages the communication between the Malmo platform and the agent itself. And then we create a mission, which is essentially the task that the agent is supposed to solve. In this example here, we will just start with a default mission, which will have no goals, no additional structures in it. It's really just a plain flat world. We start the mission, and then the key interaction between the environment and the agent is in this little for loop, or in this little while loop here. So essentially, while the world is running, we observe the state of the world. We can compute some kind of information, extract some information from this. For example, look at the rewards or the observations that have been collected so far. In the simplest first example, the agent just ignores the reward and observations, and it just sends commands to the controller. And in this case here, it sends to move, turn, and jump. And then wait a little bit and repeat. What we get is a moving, turning, jumping agent in the flat little Minecraft world. Okay. So this is how to get started. This is the simplest agent that you can create in this world. Now let's create a task that gives the agent something to do. When you create a task in this environment, there are two choices. You can start from a so-called mission XML file, which is a cross-platform format for defining a task. Or people can start through the Malmo API to create a task programmatically. The advantage of using the XML file is that the task is completely defined in this file. You can easily exchange that with another researcher to ensure that they're evaluating their agents on exactly the same task that you have defined. So I like the XML format because it's very exchangeable and easy to use. So let's take a look at what's in that XML file here. It's quite straightforward. The key components are the server section and the agent section. And if we wanted to create a task that has several agents in it, we could simply provide several agent sections. So that would then ensure that we have several agents exposed to that same environment. So if we look at the server section, we provide some initial conditions. For example, we specify what the weather is going to be like, whether we want zombies and other creepers to allow spawning. We set the start time and indicate whether we want time to pass. And all of those kind of initial server conditions are used to ensure that an experiment is easily replicable. One of the first kind of problems we ran into when starting to experiment with the platform is that Minecraft has its own physics, and there's a night and day cycle. And after about 20 minutes, the performance of our agent just kept getting really, really bad. And it turned out that after 20 minutes, that's when nighttime comes, and the vision that's provided to the agent is not very useful any longer. So you really have to make sure that you're testing the agents under the same conditions. So day and night cycle is one to look out for. Similarly, when it starts snowing, that's usually something the agent cannot deal with very well. So for now, we just set the weather to clear. In addition, on the server handler, we can provide information about what we want the world to look like. We could just take any map that is created in the normal Minecraft game and put the agent in there. Usually, we want a little bit more fine-grained control over the elements that we want in the environment. Usually, at the moment, we don't expose our agent to the full Minecraft world, but rather they interact with a small room, for example, that is more manageable to interact with and learn in from scratch. So this is something that we define here. We can create, for example, a cuboid that delimits the arena that we want the agent to be exposed to. We'll provide a floor of lava and a little bit of sandstone for the agent to look at, to walk on. There's a cobblestone beginning marker and then a blue kind of end marker. And for those who cannot parse XML so well, this is what the world finally looks like. So we have our cobblestone arena. we have a sandstone floor, and the task in this example here would be to navigate from this starting block to this end block and collect the lapis at the end. Finally, we want to provide information about what kind of agent we want to expose to this environment. As I mentioned before, we need to specify the observation handlers, the command handlers, and some kind of reward signal for the agent. Here in this case, we can see that we want some statistics about the agent. So for example, how long it's been alive. We want to see the video frame that the agent can see. So that gives us a video frame from a first-person perspective. In this case, we are providing discrete commands. So that means that the agent can move one block at a time rather than moving continuously. And then finally, we define the reward structure. So here we give a large negative reward when the agent touches lava, so when it dies in lava, essentially. And we give a large positive reward when it finds the goal, when it navigates to the goal. We also give a small negative reward for each step to encourage the agent to navigate to the goal quickly. And this is all there is. This is all you need in order to create a task for an AI agent and specify this experiment. And this simple structure, these components and the API we have created give rise to a pretty much infinite variety of tasks that an agent can be exposed to. So these are just some examples that we've experimented with over the past summer. You can create, you can create dungeons. You can create parkour-like challenges, challenges in which the agent has to climb a certain structure. Most of those tasks that we have created are still too hard for the agents that we currently experiment with to complete. But you can see how by constructing these simple building blocks, we have created the structure that gives rise to this infinite variety of challenges. And these challenges can push agents into the direction of more and more flexible learning of more and more complex tasks. If you want to try some of the capacity, some of the capabilities that Project Malmo provides, there's already a very active community around the platform. So there's, for example, a Gitter chat where people can provide help. So it's quite easy to get started. Before I move on to a kind of the learning side of agents, I just wanted to point out some of the open questions around AI evaluation. There is currently a tension between creating task instances that are very complex and difficult. You don't want to miss those reinforcement learning agents. Oh well. When we talk about AI evaluation, there's this tension between creating tasks that are very difficult, yet can be solved by engineering. And these kind of push agents in the direction of specializing to individual complex tasks. So that's comparable to creating agents that learn to translate human natural language into other languages. It's a very sophisticated task. It's a very hard engineering challenge to solve. But it doesn't necessarily push agents in the direction of general intelligence. So on the other hand, we want to develop agents that exhibit some amount of intelligence, and we need to understand what kinds of tasks we need to design in order to encourage that. We think that this requires flexibility, so we need a wide variety of tasks, but each of those tasks in general will be much simpler than the ones that we can currently solve with sophisticated engineering. It's also not clear whether there's some kind of tasks that are more suitable for demonstrating general intelligence than others. So there's a wide range of open questions around how to construct the tasks that we should be using for evaluating AI. Before I move on to reinforcement learning, I just wanted to see whether there are any questions around AI evaluation and creating tasks in Malmo. No? Everyone good? Perfect. All right. So in the remainder of the talk, I wanted to give you a brief introduction of reinforcement learning, which is one of the techniques in machine learning, one of the fields of machine learning that I personally think will be crucial in solving some of the tasks that we are currently creating. And it will be a crucial component of an agent that, if we manage to build one, exhibits artificial general intelligence. The key goal that we're trying to achieve is that an agent can achieve a wide variety of goals in complex and uncertain environments. And this requires that the agent can learn as it goes along, that it can recover from its own mistakes. So we cannot simply develop an agent that specializes and solves a certain given task, but rather we need to give the agent the necessary abilities to figure out what's going on in the world around it and to appropriately react to the challenges that come its way. So here just some of the kinds of environments that an agent might observe in the Minecraft world. And typically the interface, as I have already shown, consists of providing observations to the agent. The agent takes some kind of action in the environment, and then it observes the consequences of its actions, which we usually call rewards. So this means that the agent is typically given the task of learning about the consequences from its actions from interacting with the environment. A classic example of a reinforcement learning task is the one that I showed on a couple of slides ago. This is the classic cliff walking task, where the agent starts over here and it has to learn to navigate to this goal state over there. If we start from scratch, the agent doesn't perform very well, which is not surprising because so far it doesn't know anything about the world and the consequences of taking actions in that world. So the kind of learning that I'm demonstrating here is called tabular Q learning. It's one of the classic approaches to reinforcement learning. And let's take a look at what knowledge the agent has when it starts to interact with the environment. This is so-called tabula rasa learning. So initially, the agent is entirely naive about the environment. It doesn't have any prior knowledge apart from maybe the structure of the problem. So when the agent starts, all it knows about is this little starting square, the initial state that it's been placed in. And from trying out actions, it has to learn about the consequences of its actions. This is indicated here with those little spots at the top, left, and right, and bottom of the state. So if the agent takes a step forward from the starting state, it has experienced negative consequences. When it takes a step back, it again has experienced negative consequences. And initially here, I think it hasn't tried the left and the right action yet. Now, as the agent starts to navigate around the environment, it starts to acquire new knowledge. So it's learning that all those backward actions here along the edge of the platform have negative consequences, and it starts to learn about some actions that are better than dying in lava right away. Now, as the agent learns to solve this task, there are three key challenges that the agent needs to address. They're exploration versus exploitation, they're the credit assignment problem, and finally there's the problem of generalization. So let's look at each of those in turn and see how agents in a reinforcement learning setting deal with exactly these challenges. So to illustrate exploration versus exploitation, we can think about a maze. Whenever you are in this maze, you will only know about the consequences of taking each of those hallways by actually going there. So this means that you have to explore your environment to figure out whether there's something valuable, whether there's an action that has a very positive consequence. Before you take that last path, you won't know whether there's maybe a huge pot of gold there. So this is roughly the challenge that we're trying to solve here. The exploration part of the challenge is you need to try an action to understand what its consequences are. The exploitation is once you reasonably know what the consequences of your actions are, you want to try to take actions that give positive rewards. So there's this tension between exploiting the knowledge that the agent already has and exploring new alternatives in the case that it's missed something, it's missed a trajectory or a type of action that has better rewards than the ones that it already knows about. There's some typical approaches for balancing exploration and exploitation, and I just mentioned the most basic one that's called epsilon greedy up here. It's a very simple algorithm that uses exploration with some small probability epsilon, and the remainder of the time it simply takes the action that maximizes the reward according to the current model of the agent. So this gives us a very simple algorithm for exploring some of the time, but exploiting that knowledge most of the time. And typically in a reinforcement learning setting, the epsilon parameter of epsilon greedy is decayed to a small value so that the agent can learn and explore a lot initially, but then decay exploration to focus more on exploitation later on. So in this case here, the agent would take a random step, let's say 10% of the time, and it would take the best known action so far 90% of the time. The second challenge that the agent needs to be addressing is the credit assignment problem. So the credit assignment problem means that when an agent, let's say, steps off the cliff over here and dies in lava, it needs to understand what part of the trajectory that it has taken to get to that state was responsible for the consequence that it has experienced. So if you think about the agent when it finally manages to walk all the way to the end here, the agent wouldn't by itself understand that the whole trajectory, this full long sequence of steps, is necessary to actually getting that reward at the end there. And it needs to understand how to distribute the reward that it has observed eventually over the actions that it has taken so far. And this problem is typically solved in reinforcement learning through a dynamic programming approach to solving so-called Markov decision processes. So in the Markov decision process, we typically model a scenario where there are two components interacting with each other, the environment, for example, and the agent, and the consequences, so the rewards or the transitions that the agent experiences are partially under the control of the agent. Now, the key to learning how to act in a Markov decision process is to understand how to control the controllable part of this process in order to maximize some kind of reward signal. Typically, this is formulated as the cumulative reward. So it's we can talk about the Q value, which is the value of taking an action in a given state. And it's this infinite sum of the discounted reward that the agent observes at every step. The discount factor here is typically something close to 1, and it just ensures that this cumulative sum of rewards is bounded in some way. So the goal of the agent is to learn some optimal policy for achieving its goal in this environment. Now, the dynamic programming approach that I mentioned is often called temporal difference learning, and it's an approach for propagating rewards through a trajectory that the agent has taken to get to a certain point. Let's start with an example. So if we start with the example here, where the agent has just taken this initial step to the right, at this point, the agent has some past state S, some action A, and some new state S prime, which is the state that it ended up in. It has also observed some kind of reward, so for example, -1 for taking that step. And now the task is to update the value of taking the action the agent just took in the state that it's just been in. And this updating is done using this update rule over here, where you interpolate the current estimate of the Q value in this state and this action with the additional information that the agent has just gained. The bit of additional information is first the reward that the agent has observed, and secondly, it's the state S prime, or ST+1, that the agent has ended up in. So we can update our reward estimate with the sum of the reward that the agent actually observed at this step, plus the maximum Q value from the next step, which is indicated with this maximum operator here. So these together, R plus the maximum of this Q value, should, in a converged system, sum exactly to our estimate of the reward or of the Q value of the previous state and action. So in a converged system, they would essentially, they would exactly sum up to this. As long as the system is not converged, we can move it in this direction by exactly updating the old value with the weighted average of the current value and the new, and the new estimate we get out of the sum over here. And in this way, we propagate the experience of the agent in a way backward in time through the trajectories that the agent experiences. Okay. Any questions about this? Yeah?
It's a microphone.
The microphone. Yeah.
Thank you.
Oh, wow.
It's completely blind about the environment. Maybe they don't know that the next tile is lava or it's completely blind.
Yeah.
Why? Because you know, he can see that.
Right. So there's a difference between the observation space that the agent gets. This is kind of the classic approach where the view of the world is tabular. The agent only sees a certain amount of local information about the state that it's in and the actions that it has available. We can now expand this using the visual information to let the agent generalize to new situations that are visually similar to situations that it's seen before. And that's exactly the key to, for example, generalization using deep learning or deep reinforcement learning. And I'll explain this in just a couple of slides. So we'll see an example where that generalization happens.
Thank you.
Anyone else want the pink box? Thanks. All right. So if we take this tabular approach and we run it for about 10 minutes, we arrive at an agent that can actually navigate to the world. There we go. And we can also see how the values, the Q values of the agent have started to converge. They're not fully converged yet, which you can see as the agent is sometimes taking suboptimal paths to the goal. But as you just correctly pointed out, there's a key limitation to this approach, which is that the agent only observes very local information about the current state, the current square that it's in, and the consequences of the actions in that particular state. Now, the key question is whether it's possible to generalize over similar states that are visually similar, rather than trying from scratch to learn about the consequences of every single action, every single state. And of course, if we can generalize, then that is a much more effective way of actually learning to adapt to new situations and to use common sense knowledge to generalize to those new situations. For a long time, the theory behind this was well known, but only in 2015, with some of the work of DeepMind, were they able to actually demonstrate that learning using function approximation could allow us to generalize to new situations using the visual perception of an agent. So in the example that I'm going to show, we will see an agent that can observe its current frame that it's in, or the current visual input, along with 3 recent observations. So this is going back in time. This is the current state up here. This is the state st-1, st-2, st-3. So there's a little bit of visual memory for the agent to just reason about where it's come from, and then there's the current state. And now we can use function approximation to, using deep neural networks, to do dynamic programming with function approximation. And the key to making this work is this loss function that I'm showing up here. So the first part of this is that the problem of estimating Q values is now formulated as a regression problem. So you can see here that the problem aims to minimize the square distance between the current Q value estimate which is in parallel to what we just saw before for the tabular case, and the discounted sum of the reward, the one-step reward, and the new estimate for the maximum Q value in the next state. So this is exactly the same update target that we saw in the tabular case, but it's now expressed as a regression problem in this function approximation setting. Now, the key to actually making this work in practice was to make this dynamic programming problem look like a supervised learning problem, like a supervised regression problem. And there are two tricks that you can actually see in this loss function here that enable this to actually work. The first trick is can be seen over here in this expectation over some data that is sampled uniformly at random. The thing that is sampled uniformly at random is here a so-called replay memory. So this is some large amount of memory where the agent stores the past interactions that it had with the environment. So each entry in the replay memory consists of the state, the action, and reward observed at a time step, together with the state S prime that followed from taking that action in that state. So those are indicated over here. We have this replay memory of, let's say, 10,000 or 100,000 past experiences. And now whenever the agent makes an update to the network parameters, it samples from this replay memory uniformly at random. And this ensures that the regression problem that the agent is trying to solve is as stationary as possible. So that means that it's not affected by, for example, taking a wrong step just on that last trajectory, but rather the effects of that large amount of experience are smoothed out over time, and it's essentially a regression problem that is very close to stationary. The other component that stabilizes this problem is shown in the parameters of the model. We can see here theta ti and theta I, and this indicates that there is not a single model that the agent is learning, but there are two models. There's the model that the agent is updating and is using for taking its actions, and then there's a second model which is called the target network, which is just used to compute the regression targets of this particular optimization here. So we can see this indicated here. This would be the target network, and this target network is only updated at a very slow rate, either by swapping it out with the model network every, let's say, 10,000 steps, or it can be interpreted with the model network with a very small weight, so that it only changes very, very slowly over time. And this ensures that the target that the agent uses for solving this regression problem, again, only change very, very slowly, so that the regression problem that the agent is solving is essentially a supervised learning problem. It's essentially a stationary supervised learning problem. So those are the two key insights that actually enabled deep neural nets to be effectively used as function approximators for reinforcement learning. This was impressively demonstrated by me et al. On Atari games. In the example here, I'm showing how we can use this to have an agent interact with some 3D environment in Minecraft. So in the video that I'm going to show, we see the agent itself interacting with this room filled with some lava, and the task is to navigate to this goal in the corner here. We'll be able to see the observation, the state that the agent is in at a particular point in time. And we can also see the agent's Q value estimates. So let's run this. There we go. So it takes about 1 million learning steps, which is roughly 20 or so hours on a GPU to train the agent to achieve this goal. It's a small room, but what's impressive here is that this is some evidence that the agent has learned to generalize, to new situations. So what we see is that whenever the agent faces lava, the Q value is very negative, so it has learned that the consequence of stepping into lava is very negative. And And it doesn't matter where in this room the lava is located. This is something that is generalized simply based on visual space. So this is much more powerful once it's converged than the tabular approach that I showed earlier. It is able to generalize over the perception of the agent. Unfortunately, it also takes a much, much longer amount of time to learn this. So I mentioned previously that the tabular example takes about 10 to 15 minutes to learn. This one takes roughly a day, even though the task is still very, very small, very restrictive. So there are some key questions on how we can develop agents that learn to generalize to new tasks, but at the same time that learn within a reasonable pace. That we don't necessarily need to start them from scratch, but we want to get to the point where they can learn a new task within minutes rather than days. So there's some key open questions here. How many? 5 more minutes? 10 more minutes? Okay. So in the last few slides, I just wanted to point to some of the work that we've been doing recently. As I mentioned, one key problem is to understand how to learn agents or how to develop agents that learn much faster, for example, by generalizing over tasks right away, that can maybe learn new tasks at a rate of a couple of hours rather than having to train every agent for days before we can achieve a new task. And this was a first exploration on multitask learning using multitask deep reinforcement learning in Minecraft. So in previous work, it was shown that simply applying a network or a deep reinforcement learning agent to several tasks could result in very bad performance. For example, negative transfer, where we saw that by training the agent on 2 tasks, it actually performed worse on both than if we had trained it on each task separately. And that is given the same amount of experience. So there was some negative interference between the 2 tasks. That was well known for Atari games, where you can see that a single task network would improve over time, and a multitask network would have very low performance. Even in examples where researchers managed to train an agent to perform several Atari games, several tasks in this environment, when people looked at how those different tasks were represented internally, they found that they were very clearly separated. So you can see that here the network has kind of learned a different region for dealing with each of the Atari games individually. So there was no generalization across tasks at all. And we hypothesized that the reason for that is that the Atari games don't reflect the kinds of regularities, the kinds of common sense knowledge that we have in real world environments. We constructed tasks in the Malmo platform that address this problem. So for example, we exposed an agent to one task where it could, where it had a different action space. So one action space would be moving north, south, east, west. The other action space would be moving forward, backward, left, and right. And then we recurse whether by training the agent on both tasks simultaneously, we would be able to get agents that can actually generalize across those 2 different action sets. So our preliminary results here show that in the multitask scenario, we get at least similar and potentially better performance in the multitask setting than on training for individual tasks only. It's also very interesting when we look at the actual semantic representations that are learned, that the 2 different tasks are interleaved, they're combined with each other in the same representation. So what we saw was that there is a large kind of cluster of states that the agent can reach, both in the north, south, east, west, and in the turning action set. And there's a small cluster where the agent faces danger, so where the agent faces lava. And that again includes samples from both tasks. So we find that the agent generalizes along the lines of the consequences of its actions, rather than learning a different representation for each task individually. So this is the first evidence that using deep reinforcement learning, we can generalize over tasks and potentially have positive transfer in the multitask scenario. So this is work that we're presenting at the European Workshop on Reinforcement Learning tomorrow, I think, tomorrow. and at the deep reinforcement learning workshop at MIPS as well. Another line of work is in understanding the capabilities, the characteristics of the agents that we have actually developed. So the work that I'm pointing out here had the goal of measuring certain aspects of the ability of an agent without having to know what kind of architecture the agent actually has. So this could be useful if we wanted to, for example, measure some kind of capabilities of biological agents and AI agents, because we can just use the observed behavior of those agents to compare them, rather than having to know some kind of deep underlying aspects of the architecture or the kind of approaches that each of the agent would use for solving certain tasks. The idea here was to quantify the amount of memory that an agent uses by measuring the flow of information from the past experience of the agent to the actions that the agent takes in the future. And we developed an approach that uses estimates of mutual information between those quantities in order to quantify what amount of memory an agent uses at each point in time whenever it makes a decision. Just as a kind of proof of concept example, here we can take, for example, a T-maze or a maze where the agent has to observe an initial queue in order to know which goal state it has to move towards at the end of the maze. So in this case here, when the queue is green, it has to move to the silver block here. If it were blue, then it would have to go to the golden block. So for the majority of the agents performing the task, the agent doesn't need to know anything about its current, its environment, except whether it needs to move forward or whether it needs to move to the left or the right. And the precise point that the agent needs to use to make that decision of moving left or right is at that past observation where it observed the queue. So we can see when we have an agent that shows optimal behavior in this environment, we see the memory estimate to spike at exactly the right point in time where we expect the agent to access the queue that it needs to make that decision. So in the talk I gave you an overview that started with the quest for artificial intelligence and how Alan Turing's thinking kind of influenced the research that was to come and that still influences the research that we do today. I looked at how Project Malmo provides the building blocks for creating a huge variety of complex tasks for AI experimentation, and how from those building blocks we can move towards more and more complex tasks and experiments to evaluate AI agents on. And then I moved to an introduction of reinforcement learning, where I kind of gave an overview of some of the key concepts that reinforcement learning agents need to address. The problem of balancing exploration exploitation, the credit assignment problem, and finally the problem of generalizing, for example, from visual information to use to learn common sense knowledge and to learn to interpret its environment. There are a huge number of very exciting research directions moving forward, and just indicating a few over here. There are challenges in coupling, for example, reinforcement learning with language representations of the world, or with understanding how to connect language to the visual representation that the agent perceives. There's obviously a very active research area in coupling reinforcement learning with deep learning, and we have only scratched the surface of what's possible in that space. It's very interesting to look at how this interactive learning and decision-making could be coupled with, for example, reasoning processes that allow the agent to look into the future, as well as learning from its past experience. Finally, the area that I'm particularly excited about is the question of how we can develop AI agents that learn to collaborate, either to solve tasks collaboratively with other AI agents, but also how we can train AI agents to collaborate with humans and to help us achieve our goals more effectively. With that, I want to conclude my talk. I wanted to finish with pointing out that Project Malmo is available on GitHub. It's very accessible and easy to try it out today. So go and have a look. Thank you very much.
Okay, thank you, Katja. Do we have some questions about the platform, the techniques? Don't be shy. Huh?
Okay, sorry. Maybe I lost that. The platform is free, or you need to buy Minecraft in order to program that?
No, it's free. You just you install the prerequisites as per the instructions.
But you need to have installed the Minecraft.
The client.
The client.
It's part of the platform. It uses the modding framework, so you can actually you just go to the download the platform and it installs itself. You don't need any. So for single agent missions, you don't even need a login. You just run it locally. You can just get started right away. For so-called multi-agent missions, we currently need a login because it's it's logging in additional agents through the authorization server. So for multi-agent missions, a login is required.
And the second thing, but maybe I've lost because my English is not very good. You have explained how do you have generalized the knowledge, the visual knowledge? How did you generalize this knowledge?
Right. So the generalization happens through the function approximation of the deep neural network. So there the key is that the agent needs to find regularities in the visual space. So for example, it needs to learn that whenever it faces lava, that is the key indicator that something dangerous is going to happen, rather than all of the other things that are going on in the visual scene. Because neural networks are so good at finding patterns in visual information, this is why they're very, very, very effective at learning a representation that can generalize over the visual space. An aspect that is still very poorly understood is how we could generalize in the action space. So for example, how we could understand that a plan of moving to the goal in this direction is very similar to taking a slight detour, and how exactly those trajectories relate to each other. So generalization in the visual space is roughly solved by using deep neural networks as function approximators. Generalization in the action space is still an open problem.
Okay, thank you.
Hi, and thank you for the talk. Do you know about the current state of multi-agent support? Because I remember reading that there are many problems with this.
Yeah, so if you move to multi-agent scenarios, many assumptions that current approaches make break right away. So for example, the Markov assumption might break if you interact with an agent that learns at the same rate as the other agent, because some of the approaches that we're using here require that you can go back to any previous state as often as you want and explore over consequences of actions in those states. If your opponent has learned and doesn't allow you to go back to that earlier state, then there is no way for the agent to actually return to that earlier state. So we need to be able to deal with, for example, adversarial behavior rather than a purely stochastic environment. And that, I think, is one of the key challenges in making these kinds of approaches work in multi-agent scenarios. The majority of current multi-agent scenarios try to use tricks that essentially reduce the problem again to a stochastic setting, for example, by qualifying how much the opposing agents have to explore or how much they have to behave randomly over some distribution. And that allows us to make progress in those kind of subsets of the full multi-agent problem. But the full multi-agent scenario is not very well understood yet. There's some very interesting connections to game theory which could be explored there. But again, that's an active research area.
Yes, hello. So after having built this platform on Minecraft, have you discovered some things that you don't like in Minecraft, that you would have preferred, that it was different, you know? And do you have an ability to influence how Minecraft develops to suit your goal of having a platform for AI experimentation better?
Great. Let me answer in 2 parts. In terms of kind of advantages and disadvantages of the platform, there are some kinds of experiments that the platform is great for, and there are others that it's not very great for. If you wanted to, if you're going for pure speed, then the platform is not ideal because it has the full Minecraft server. It has to actually run, all the physics of Minecraft in real time. So that is a lot of computational overhead if you just wanted to run classic tabular reinforcement learning. So it's not the right environment for trying something as a proof of concept very, very, very quickly. If you need, let's say, to run millions of steps in half an hour, that's not going to happen. It is fantastic for this kind of more flexible learning where we push towards more and more real-world scenarios that require real-time interaction with many agents in a flexible set of tasks, and where it requires integration, for example, of visual information and language. That is something where it's uniquely useful for. So in general, the advice would be to understand what experimentation is required, and then pick the right platform for that. In terms of influencing Minecraft, this is an effort that's completely independent of Minecraft. It's really a research project that we do for understanding what is needed in AI research and catering to that research and academic audience. We are talking to the Minecraft team, of course. They're really excited about the fact that we're doing this, but what they do is independent of what we do. Maybe eventually, if we develop an AI agent that does something awesome in Minecraft, there might be a possibility for integrating that with Minecraft, but this is not something that we're discussing right now.
Thank you.
Hi, it was a very interesting talk.
Thank you.
Is there any way that an agent can not start from the scratch?
That's a very good question. We have done in the past experiments on imitation learning, where we would learn from expert trajectories. That works very well. So I think if your goal is to build the best possible agent at this point in time, then it would start from supervised learning of imitating an expert policy, and then continue that learning in a reinforcement learning style setting. So this bootstrapping from prior information definitely is one of the key approaches to making something that scales to complex tasks.
Thank you. Come on, boys.
There's a very brave corner in this, in this part of the room.
No one? Back to you then.
I can say something about the good things about Minecraft. As even in Cambridge, you can set the weather as stable. That's a real feature. I have a question, perhaps, for students. You present Malmo as not only as an AI evaluation, but AI experimentation. So I think that you are considering the idea of using the platform for teaching as well, not only for research. So for instance, your first example about Q-learning, I think that, well, you can teach Q-learning with any flat world, but I think that for students might be more interesting if you are having your first class with enforced learning, that you can teach, and you can do that with your Minecraft. Are you planning at Microsoft Research to start some kind of program with universities in terms of teaching AI with Malmo?
So interestingly, the teaching aspect is not something that we envisioned when we started the project. I don't know how we could have missed that, but we weren't thinking about that at the time. Since we released the platform, we've heard from a large number of high school students who use the platform for learning programming, for learning about reinforcement learning. We know from a couple of universities that are using this in undergraduate and graduate courses for AI courses. So for example, recently someone from the University of Glasgow got in touch and told us that they've been running their full course for the past couple of months purely based on Malmo. So it's really exciting to see all this activity around using this in teaching going on. people are kind of going off and developing their own kind of course materials, which is great. So there's a lot of growth and a lot of use of the platform already. At the moment, my team doesn't have the bandwidth to really focus on the education side. So in some sense, we're just looking to see what kinds of uses, what kinds of materials people come up with, and we're very excited to support when something is needed to be added to the platform. We are looking at encouraging students to try some new ideas for some reinforcement learning with the platform. And we do have plans to create a challenge for students to explore new ideas in this platform. So we are looking to engage more with the student community than we have in the past. We probably won't be developing kind of course material on top of the platform in the future.
Thank you. Do we have? Yeah.
Well, maybe this is just something personal about me, but this has been my first connection with AI, artificial intelligence, and I feel like you encourage us to engage with it, but how can we learn from the beginning with this? Maybe are there in the platform any kind of tutorials or something?
Yeah, great question. So the platform comes with a set of 7 tutorials. They're currently all in Python, and they kind of take you through the steps from the simple agent 101 that I showed on that slide to agents that can dig and that can achieve a small goal within the Minecraft world. So I think in terms of learning, that is the best starting point to just go through those tutorials and try to solve them. The next step from there is the best next step there, I think, is to engage with the community. So the Gitter channel that I mentioned is a great place for discussing ideas, kind of seeing what kind of things others come up with. Recently, I've seen people post YouTube videos of the agents that they have trained and kind of giving us an idea of what they've tried. So from the tutorials, trying things out and engaging with others in the community are the best next steps to kind of learn more about this space.
Thanks.